1851 microprocessor and our microcontroller. The standard 1851. This is the 8-bit microprocessor presented by the Intel, as I said before, and it is very popular, and it is a family. What is family means? In this family we have many kind of microcontroller. Okay, not only one. 1851 family has many kinds of microcontroller. So if you need a microcontroller, first of all you have to specify your needed units. Then, according to those units, storage area and as like that, according to those information, you have to select one of them. Why will we learn 1851 in this lecture? It is popular, so we have many sources. Some family producer, Intel, Atmel, Philips, AMD, Infineon, Matra and Dallas Semiconductor, some of them. It is popular, so we can find many internet web pages, books, technical documents and as like that. Convenient, fast and powerful. 1851 core architecture is very fast and powerful for control applications, common usage and compatibility. Although there are many different products, all products are compatible at the binary code level. So if you know a programming language for any 1851 member, you can use another members if you need. Also, we can say it development continuously. The first produced in 1980s, but nowadays we know it. Some of the members, including 16-bit models, can be easily supplied in different capacities, sizes and prices. The main feature of the 1851 microcontroller are 8-bit CPU for the control applications, ability to perform intensive Boolean operations, 64K program memory, 64K data memory, 4K on-chip program memory, 128-byte on-chip data RAM, 32 bidirectional addressable input or output lines, 2 16-bit timer or counter, full duplex UART, on-chip clock oscillator. This is a standard 1851 architecture. What we have, interrupt control unit. Some of the sources is internal and some of the sources are external for the interrupt. We have two interrupt source as a timer here. For the serial port we have one source. We have also two external source for the interrupt. Of course we have 1851 CPU, oscillating and timing unit. For this unit we need a crystal between the XTOL1 and XTOL2. 4 kilobyte program memory, as you see. SFR means special function register. We will see in detail next. 128-byte data memory in here. We have two counter, timer or counter, timer counter 0 and timer counter 1. This is common bus, as you understand. Common bus control unit, input output ports. We have 4 ports, as you see, and serial port. We have 2 serial port input, transmitted data and received data input. For the common bus control, we use AIL and PSEN pin, which we see next. And this is our microcontroller. And what is the difference between the 1851? These blocks are highlighted in yellow. For example, in here we have a difference. The standard 8051 4 kilobyte, but here we have 8 kilobyte. For standard 1851 we have 128, but here 256 byte data memory, low RAM area and high RAM area. The standard has 2 timer or counter unit, but we have also another timer or counter unit. There's our difference between the 1851 and 1852. Sorry, this is not our microcontroller. This is 1852 core. But we have to know this 1852 core is convenient and is a member of the 1851 family. Okay, 1852 is not a new family. Our microcontroller now, we have some another advanced features. Yes, this is important information. When you see a data sheet for any microcontroller, if it has a member of any family, you can find an information about it. For example, for our microcontroller compatible with MCS 51 products. MCS 51 means 1851 family. Okay, this is another expression to express it. So we can understand easily that this is a member of the 1851 family. Okay, 12 kilobytes in system programmable flash program memory, SPI serial interface for program downloading, endurance 10,000 write erase cycles, 2 kilobytes EEPROM data memory, 2.7 and 5.5 operating range, full static operation 0 Hz to 24 Hz, megahertz, sorry, 3-level program memory lock, and blah blah. We have 256 byte RAM. It is 128 for standard 1851, as you know. We have 32 programmable input-output line, 3 16-bit timer counters, 9 interrupt sources. For the standard 1851, as you see here, we have 5 interrupt sources, 1, 2, 3, 4 and 5. But for our microcontroller, which is compatible with the 1851, we have 9 interrupt sources. Enhanced UART serial port with framing error detection and automatic address recognition, enhanced SPI serial interface, low power idle and power down modes, and blah blah. You can see another specification. For our microcontroller, we have some different kind of processor. Yes, we have some different kind of processor. It is the first one. As you see here, we have 40 pins for this one. From 1 to 8, we have port 1. Okay. In 9, we have a reset input here. From 10 to 17, we have port 3. 18 and 19, XTOL 1 and XTOL 2. Why we need it? Crystal inputs. 20, we have ground pin. From 21 to 28, we have port 2. 29 to 31, we have PSAN, ALE, and external access pin, which all of them will be explained in detail. From 32 to 39, we have port 0, and the fourth pin is VCC, which is supply voltage input. Okay, this is this configuration, DIP configuration. Another configuration, PLCC, as you see. In this configuration, we have 44 pins, SMD type configuration. And we have another configurations, TQFP, it is SMD again. And the last one is as like that, 42 pin. In this lecture, we will talk about this configuration. Okay, because in the lab we have an experimental board which is used this configuration. But I have a question now. For example, in here I said port 1, but some of them are another expression. What they can be? Yes, some of them is sending or receiving data. Okay, as the same way you can see in the port 3, RxD, TXD, int0, int1, T0, T1, writing and reading pin. So we can use these pins as port and also some another duty. Okay, we have to know this. Okay, let's start to the architecture. Some peripherals on chip. We have 4 8-bit parallel input and output, which is called as port 0, port 1, port 2, and port 3. These are special names of them. We can use these ports as input or output ports. Okay. Why we use the ports? Ports or pins enable the transfer of the logical data 1 or 0, or you can also think of as on off between the physical world and the microcontroller. Okay, when you want to send any information to the microcontroller, of course you have to use ports. If you want to get any information from the microcontroller, so you have to use again ports. Okay, so it is a communication device for the physical world and microcontroller. 4 times 8, we have 32 inputs or outputs, and each of them can be operated independently. It is important. We can use each of them independently. For example, port 0.3, port 0.4, port 3.3, it means the third bit of the port 0, fourth bit of the port 0, third bit of the port 3. Okay, each of these bits can be checked with these symbols. We can use these symbols for the bit-based operation, or also you can do byte-based operation using port 0 or port 1 or port 2 or port 3.3. If you want to use port 2.5, you can use this symbol. Okay. One of the most important features of the 1851 is that it can do bit-bit operation. Bit-bit operation. It provides a lot of convenience in cases where bit processing such as control is required. By using the 32-bit, we can do 32 on-off control, for example. After the reset, this is so important. After the reset, port 0, port 1, port 2 and port 3 registers are loaded by the hardware with FFX. Okay, what is mean FF? As you know, all registers are 8-bit for our microcontroller. FF means all of them will be 1. Okay. After the reset, all ports will be loaded FFX. This is the our microcontroller block diagram. We have a supply voltage and ground pin here. Port 0, port 2 here. All ports we use some latch, which we'll see in detail later. Again, port 1 latch, port 3 and port 3 latch. Xtol 1 and Xtol 2 here to connect between crystal to produce a clock piece, watchdog unit, timing and control unit. For this unit, PSAN ALA proc used as output, as you see, and EA and reset can be used input for the microcontroller, because as you know, this area is physical world. Okay, instruction register here. We have dual data pointer, SPI port, program logic. What we have also, yes, program counter, PC incrementer. In the fetch and execute cycle part, I said to you when the opcode obtained, so we can understand we have also another operand. For getting this operand, program counter increased by 1 by the hardware. In here we have PC incrementer doing this operation. Okay, buffer, program address register, stack pointer. We didn't see before, I think. Program status word we didn't see, I think. What else? Accumulator, ACC means A. It can be represented with the ACC also. Temperature, sorry, not temperature, temporary unit. Okay. B register, EEPROM, address register, RAM, and flash, and blah blah. This is our microcontroller block diagram. One serial input output. A separate transmission line is required for each bit in the parallel communication, as you know. But if you use serial communication is provided by only a data line. You can send an information, and after the some time you can send another data. So this is serial communication. The current parallel data is translated into parallel data with intermediate operation, and communication is provided over only a line. So how can you evaluate the serial or parallel communication? What are the differences between them? For the parallel communication, for each bit you need a line, but serial communication you have one line, but you can send all of this information in a time range respectively. Because of using the more line, the parallel communication is of course costly, but the parallel communication is faster than serial communication. Okay.